Welcome to ASOC Tutorials India program again, and in continue to the previous session, today I am going to give oscillators an overview. Before I start this session continuously, kindly refer to the previous session. Whatever you have remember, Inductance Explained Part 1, it is SD17A. In mutual inductance transformer explained part 2, and various parts of inductance, impedance, resonance, series parallels, basic knowledge of LC filters, basic of amplifier, because they are all base of oscillator. There is a very negligible difference between amplifier and oscillator. So once you remember all previous session, then it is advisable to continue to today's session, and today's session is on the oscillator. Oscillators are an electronic circuits, or I can say devices, that generate an output signal without the necessity of an input signal. In other words, I can say this circuit itself generates a specific required or desired frequency with desired wave shape, maybe sine wave, square wave, rectangular wave, and whatever the need as per the device or system. So first I want to tell you this oscillator produces a periodic waveform on its output with only the DC supply voltage as an input. This output voltage can be either sinusoidal or non-sinusoidal. When it comes to non-sinusoidal, already I had told you it is rectangular wave, square wave, sawtooth wave, and so on. So just this keep it in your mind. When we are using a device or oscillator, DC is coming and output is desired output of specific frequency. So when it comes to sinusoidal or sine wave oscillators, this is based on the principle of positive feedback. Just note down positive feedback. This is the objective question, where a portion of the output signal is fed back to the input in a way that causes it to reinforce itself and thus sustain a continuous output signal for infinity till the DC available. These oscillators are widely used in most of the communication system as well as in digital systems, including your computer for time clock to generate required frequency and timing signal pulses, and in transmitter receiver everywhere it is required. Oscillators are found in many type of test instruments also, those used in laboratory also. There are two major classification of oscillator. Note down it. One is feedback oscillator, that is working on feedback, and second relaxation oscillator, which is working on RNC charging and discharging circuits. When it comes to the feedback oscillator, first one, which returns a fraction of the output signal to the input with no net phase shift, resulting in reinforcement of the output signal. Its mean it will boost the signal. A feedback oscillator consists of an amplifier for gain and a positive feedback that produce phase shift and provide attenuation. So this system required an amplifier and output we are taking as an input with suitable feedback circuit and phase shift so that it can give continuous output and maintain a standard, a fixed value. Otherwise it will be called a dump waves. So now coming to the relaxation oscillator, second one. This one oscillator, instead of feedback, a relaxation oscillator uses an R resistance, C capacitor timing circuits to generate a waveform that is generally a square wave or other non-sinusoidal waves. Typically, a relaxation oscillator uses a Schmitt trigger or other device that changes state, alternate or toggle, or create a capacitor charge and discharge through a resistance, and combination of two decide the frequency. Feedback oscillators operation is based on the principle of positive feedback. This just you note down. And feedback oscillators are widely used to generate sinusoidal waveform. Same principle. In positive feedback, a portion of the output voltage of an amplifier is fed back to the input with no net phase shift, resulting in a strengthening or giving the gain to the output signal. You see on right side a feedback portion is generated which is including phase shift, and the in phase feedback voltage is amplified to produce the output voltage, which in turn produce the feedback voltage. Here two terms are coming, in phase, out phase. In phase I am going to explain you, out phase I am not going to explain you. When the time comes I will discuss. Same way, a loop is created in which the signal maintains itself and a continuous sinusoid is produced. You can see right side, a loop is already created, output is being fed back to the circuit to maintain a continuous output, and this value, this frequencies depend on feedbacks and RC and other parameters, and this phenomenon is called oscillation. Continuous generation of frequency is called oscillation. This one keep it in your mind. So going next, the difference in phase or out phase is just feedback circuit, they are 180 degree out of phase. Two conditions are required to sustain state of oscillation, this phenomenon. What two conditions? First, the phase shift around the feedback loop must be 0 degree or 360 degree. It must be equal. Second, the voltage gain around the closed feedback loop must be equal to 1 or unity. If it is less than 1, it is damped wave, slowly it will be 0. If it is more than 1, slowly gain will go high and it will be distorted. So keep it in mind, gain should be unity, so that this output must be maintained as a standard output, no distortion, no damped. Three type of feedback oscillator. Normally they are used RC circuits to produce sinusoidal output, and they are Wien bridge oscillator. First one I am going to discuss today. Phase shift oscillator. This is another one also going to discuss. 20 oscillator, two oscillators of RC working in parallel. Generally, RC feedback oscillators are used for frequency up to and about 1 MHz. Note down this point is very important. RC feedback oscillators are used for frequencies up to 1 MHz. And this Wien bridge is maximum use of oscillator for wide range of frequencies. And this feedback circuit, Wien bridge, use lead and lag circuit. How they use lead and lag circuit? Just see the diagram. One RC in series and one RC in parallel. First R1 and C1 together, they form the lag portion. See this R1 and C1, they are lag portion of the circuit. On other side R2 and C2. See on diagram, black color, R2 and C2. They are forming the leading portion. So these two circuits are working together, leading and lagging, and generating a required desired frequency to produce a frequency. this is called relaxation oscillator, and this is how the output is coming. This is a response curve of this RC feedback circuit going continuously. This feedback oscillator use RC up to frequency of 1 megahertz, because after that it is not stabilized, and the output is sine wave. Just one thing I want to tell you, for phase shift oscillator we can use operational amplifier. ASOC exam may be not asked about operational amplifier, so I am not going to cover it. I am using FET, field effect transistor. I have already covered in previous sessions. BJT, bipolar junction transistor, also I have covered in previous session. Not going to cover in detail because this is already you have in previous session. And 20 oscillator, this one I am going to cover today. And other type of oscillator which use LC feedback circuits, they are normally use inductance and capacitance for higher frequency, more than 1 megahertz, more than 1 megahertz, note down it. So this kind of feedback circuit using LC or tank circuit is preferred for higher frequencies. And examples are Colpit oscillators, Hartley oscillators, Armstrong or tune collector oscillators, clap circuits. So this one also I had covered in my previous session. So kindly go through previous session, not going in detail because they are part of resonance and LC circuits. So continue on my topic, and first I am going to cover Wien bridge oscillator. The basic Wien bridge uses the lead lag network in the positive feedback loop to select a specific desired frequency that is amplified. Already explained you in previous slide. This one. The voltage divider in the negative feedback loop sets the gain to make up the attenuation of the feedback network, like amplifier class A, B, AB and C, if you remember. This Wien bridge oscillator circuit can be viewed as a non-inverting amplifier configuration with the input signal fed back from the output through the lead lag circuit as shown left side down. This is the basic network shown at down, and this is feedback circuit. You have to understand. To start the oscillations, an initial closed loop gain of the amplifier must be more than 3 to achieve at least some desired output, which will be sent back to amplified, and after that the gain will make as a uniform 1, because if it is less than 1 it will be damped wave, if it is more than 1 it will be distorted waves. So that you keep it in your mind, and the gain of the amplifier here must later decrease to 3 so that the total gain around the loop, this entire circuit, must be 1 and uniform to sustain the output oscillation. This is required. Going continuously. The next one is the phase shift oscillator. This one you have to understand. The phase shift oscillation uses 3 RC circuits. You can see left side, and these 3 circuits feedback path have a total phase shift of 180 degree at one desired or specific frequency. For this reason, an inverting amplifier is required for this circuit. Each of the 3 RC circuits in the feedback loop, you can see in box shown, can provide a maximum phase shift of approaching 90 degree. And this oscillation occurs at the frequency where the total phase shift through the 3 RC circuits R1, C1, R2 and R3, C3 become 180 degree. But same time if you observe, R3 is being used as a feedback non-inverting input. and RF, reference frequency, is direct feedback. This inversion of the operational amplifier itself provides the additional 180 degree to meet the requirement for oscillation. So 180 plus 180, 360 degree or 0 degree phase shift is around the circuit will start oscillation. And the condition for oscillation with the phase shift oscillator is that all R and C should be equal. If they are not equal, the wave shape will be disturbed and different, unequal. The amplifier must have a gain of at least 29 to make up for attenuation of the feedback circuit. It means this RF resistance divided by 3 should be more than 29 of the gain. This one you keep it in mind. Not going in detail because this is not required, but you have to understand it. Going continuously. Now the next one is the twin T oscillator. As the name is twin T oscillator, you can see left side two resistance and one capacitor, and other one two capacitor with one resistance, one with low pass and other with high pass. They are working in parallel to provide a feedback circuit. So this 2T type RC filter use as a feedback loop. You can see left side. This box is showing clearly. Inside, if you see, there are two feedback circuits, one low pass, one high pass. One of the twin T filter have a low pass response and the other one has a high pass response, as already I am explaining you. The combination of these two parallel filter produce a band stop or notch response with a center frequency equal to the desired frequency of oscillator FR. So these two filters generate a desired frequency. Oscillation cannot occur at frequency above or below FR. So this frequency will generate an FR frequency. Because of the negative feedback through the filters, at HR, however, there is a negligible negative feedback. So feedback is very low because this is filter circuit. Thus the positive feedback through the voltage divider R1 and R2 allowed the circuit to oscillate. If you see other side R1 and R2, they are oscillating this amplifier circuit or oscillator circuit. But the frequency is being generated by low pass, high pass, this twin T filters. This oscillator is called twin T oscillator. Not going in calculation detail, but this is also a very good filter. Going continuously. The basic twin T oscillator combine a low pass and a high pass filter to form a notch filter at the oscillation frequency already shown in box. An excellent notch filter can be formed by using R's and C's related by a factor of 2 as shown in left. So R using equal and C is 2C, and downside you see C and C, they are in series, and R1. This is the value of resistance of R and C to generate a frequency, and they should be uniform. With this relationship of R and C, the oscillation frequency is approximately decided as a FR is equal to 1 by 2 pi RC. Already these numericals you have done in previous session. Same way you have to understand, and if need you can calculate it. So going next, relaxation oscillator. This relaxation oscillator is basically depend on resistance and capacitor charging and discharging. In other words, I can say relaxation oscillator make use of RC timing and a device that changes states to generate a periodic waveform, but this is non-sinusoidal, means square wave, rectangular wave or sawtooth wave. Here you need to learn timer IC 555 also, multi-vibrators also. Multi-vibrator may be stable or free running, monostable or one shot multi-vibrator or bistable or flip-flop. This one I am not going to explain you, but if I get the time, surely I will cover it in future. So remember the previous classes on LC oscillators already I have covered in tank circuits. So RC feedback oscillator, particularly the Wien bridge, are generally suitable for frequency up to 1 megahertz. Note down. And LC feedback elements are normally used to oscillate that require more than 1 megahertz, higher frequency, especially intermediate frequency, radio frequency, video, and others. But again, LC oscillator also have a limitations. We go to the crystal oscillators. But here you have to remember the frequency limitation. Lower unity gain of frequency of the most operational amplifiers, transistors, BJT or FET are often used as a gain element in LC oscillator. These components are used for only to improve the gains. Several types of resonance LC feedback oscillators like Colpit, Clap, Hartley, Armstrong and crystal control oscillators are exist already explained in previous session. So next one is crystal oscillator. It is more stable, much better and more accurate, and it is using on the principle of piezoelectric crystal as a feedback loop to control the frequency. This quartz is a type of salt, is one type of crystalline substance found in the nature that exhibits a property called a piezoelectric effect. When a changing mechanical stress is applied across the crystal, this is caused to vibrate. A voltage develops at the frequency of mechanical vibration. And conversely, when a AC voltage is applied across the crystal, it vibrates at the frequency of the applied voltage. This is a standard structure. When you press it, frequency will come. When you give frequency, it will give vibrations. The greatest vibration occurs at the crystal's nature resonant frequency, which is determined by the physical dimensions, thickness and other parameters, and by the way the crystal is cut. Not going in detail for crystal oscillator, already I have explained you, but here I advise you, please go through your books and notes for more details. My session is just about an overview, and that overview of oscillators giving you in this session. And now it is just time for multi-choice question. I hope you are ready for MCQ. Oscillators operate on the principle of what? A. Positive feedback, negative feedback, signal feed through, attenuation. Your time start now. 10 seconds. Choose the right answer. Yeah, positive feedback. I told you several times, note down it. Oscillator work on the principle of positive feedback. So some explanation also I have given to you on screen. You can read it. Going to the next question. Which of the following oscillator can be used where high stability of frequency is required? High stability. Crystal, Wien, Hartley, Colpit. Your time start now. Crystal oscillator. Already I told you crystal oscillator is more stable form of oscillator. And in crystal oscillator there are advantages also and disadvantages also. You can read it. I have already mentioned on your screen and also explained in previous slides, previous sessions also. Going next. A Colpit oscillator generate what? Square wave, sine wave, sawtooth wave, damped wave. Your time start now. Sine wave. All LC type tank circuit type filters produce sine wave. So keep it in your mind. So this was a good answer, good try by you. And this is an end of today's session, oscillators and overview. I hope you like it. If you like it, kindly subscribe to my channel. And now see you in next part. Have a nice day. Bye bye.